Well, welcome to our first Lunch and Learn this week. Glad you could be here. Hopefully what I'm going to share with you will be helpful. And don't be afraid to ask questions, especially at the end we can talk about stuff in real detail. So what I'm going to talk about today is what we call dynamic pattern simulation, and specific for electron backscatter diffraction patterns, or EBSD patterns. And that's me, but I haven't done all this work. In fact, I've done very little of it. I'm piggybacking on some work from other folks. But what I want to do is give you, first off, an introduction, and then talk to you about some of the tools that we've started to put into our OIM analysis software, which is our post-processing software for EBSD. And in specifically three areas: dictionary indexing, which you may have heard about. It's been talked about at this conference and other conferences. And it's kind of an exciting new area in some areas, in some applications. And then I'll talk to you about reflector optimization, which I'll explain, in background simulation as well. So, like I said, this isn't work that we've done specifically, but we're piggybacking on top of some really good foundational work. The first paper in this area was by Imo Winkelmann, and then another group at Carnegie Mellon University and Mark de Graaf's group. They've done a lot of work here, and this is the group I've been working with to try to improve what we're doing. So in terms of dictionary indexing, once again, it's Mark's group. You can see he's kind of the last author on several of these. And then myself, I've been involved directly on these reflector optimization problems. So in terms of an introduction, traditionally with EBSD, we've used kinematic simulations to try to predict what reflectors we expect, to help us understand the diffraction problem and the diffraction patterns that we get. And we use a pretty simple approach. It's based on structure factors where you know the positions of the atoms, you know the planes in your crystal, and so if you do a quick calculation, you can come up with what we call a structure factor, and the intensity of the bands is then reflective of that structure factor. So for example, I have these reflectors here, a list for probably FCC, something simple, and you can see the structure factors there. And so the bright bands you see in that pattern are related to those structure factors. And that's a basic way to do it. But you can see a real pattern doesn't look a lot like a kinematic simulation. It gets the basic location of the bands, which is important from the geometry point of view, but it doesn't really tell us the intensities don't match up. The bandwidths match up pretty well, but other than that, it doesn't really look like the patterns themselves. So the way we get around this is something called dynamic simulation, and when we talk about that, we're talking about the interactions of the incoming electron beam with the electrons in the crystal. And with the kinematic, you can kind of think of as a beam coming in, hitting an atom just right, coming back out. But in reality, we've got other interactions going on. We've got electrons coming in, hitting multiple atoms. We've got scattering going on in all directions. And dynamic pattern simulation tries to take these things into account. So we start off with a Monte Carlo simulation of 2 billion electrons within the crystal structure. We don't really think of the beam as coming in. We think of it almost an infinite source of electrons within the sample itself trying to come out. They do get in there through the beam, but it's the exit that we care about, not so much the interaction coming in. It does affect things a little bit, but that's a little more complexity than we really want to deal with. So then from those Monte Carlo simulations, we construct what we call a master pattern. And you can think of it really as a pattern that covers the entire sphere. But because of computers, they like nice square grids of data, so we use what's called a Lambert projection to take the sphere into a square result. We call it the master pattern. So then once that covers a lot of different situations, but what we need to do is construct an individual pattern, and we can do that for any given EBSD detector geometry and sample tilt to a certain extent. Some of the sample tilt's already in the master pattern calculation. But we can do any detector geometry and crystallographic orientation. So what that means is this is a really big calculation to get the master pattern. So for something like a cubic on this computer we're using here, it might take us 3 or 4 hours. If I wanted to do something more complex, like a geological material, it might take a weekend, running full bore on a GPU, all the bells and whistles. It's a big calculation. But then these individual patterns, we can once we have the master pattern, that calculation's quick, relatively quick. So that's kind of the basis. To show you an example, here's an experimental pattern, the dynamic simulation, the kinematic simulation. Clearly our dynamic simulation is a much better match. It even captures some of the fine details around the poles, the zone axes. It captures a lot of details. So now we can start to understand some of the physics that's going on in these patterns, which I'll come back to. So the simulations are good, but if you want to look at the details, they're not perfect. So for example, if I were to do that band there, if I look at the band profile, the one on the left is an experimental pattern, the one on the right is a dynamically simulated pattern. You can see it's much cleaner and nicer, so that we're not capturing all the details. We know what some of those things are. In this case, it's an absorption effect, but we're going to ignore those kind of for speed, especially when it comes to dictionary indexing. We can do a little better with the kinematic. I've kind of given you kind of the worst case example, and that's because we only consider those reflectors we use during indexing, which is important for indexing. But if we really wanted to try to simulate, we'd use something like this, where we'd try to use all the bands in the pattern, try to capture all of them, and it starts to look more like a real pattern, but it's still not perfect, as you can see there. So once again, on the left is the experimental pattern, the one in the middle is the dynamically simulated, the one on the right is the kinematically simulated. And just to point out, the examples I've shown have been for nickel. That's a nice easy one to do, but we can do a little more complex things. I have a poster tomorrow on feldspars. We've been looking at simulated patterns in this mineral series, trying to understand better how the mineral crystal structure and the patterns are related to each other. And just to let you know, this isn't just in the on my desk. We actually have this in our OIM analysis software, just some screenshots of what that looks like. So this is something you can play with now within our software. All right, that's nice. Pretty pictures. We all like pretty pictures. This is a microscopy conference, but what are we going to use this for? How are we going to use this to get numbers and learn more about microstructures in our materials? So the first one I'm going to talk about is something called dictionary indexing. So the idea of dictionary indexing is we're going to create a pattern from our simulated master pattern at each point in orientation space. Okay, and that's kind of a difficult thing to do because orientation space is a big continuous space. You could create infinite number of patterns, but we're going to take some kind of sampling of our space, say every 2 degrees, for example. And so this is an example here of all the patterns we calculated. And so we do this for all of orientation space every 2 degrees. And then what we're going to do is we're going to take an experimental pattern, compare it to all patterns in the dictionary, and find the one which matches that pattern the best. These dictionaries are large, which I'll get to, and that's an important point. But you can do this and get a best match. And so it's another way of indexing. If you've used our software, you're familiar with the Huff transform, finds the bands. We use some geometrical arguments we call triplet indexing to get to the correct answer. In this case, we're just doing a match. We're just trying to find the best match. So there are some things we need to be worried about. First off, we need to try and cover all of orientation space in a somewhat uniform way. That's actually somewhat impossible, but we're going to do our best using something called cubic choric sampling. You could do this in Euler angles, but which is what we've done here, but you could use any representation of orientation you like. The goal is we enter a target spacing and then we calculate patterns for every orientation a certain distance apart. So here's an example. This is every 15 degrees in what we call Rodriguez space. And you can see it's pretty sparse. As I go to 5 degrees, you can see there's a lot more points. As I go to 2.5 degrees, it's a lot of points. If I went to 1 degree, it would just be black. You really wouldn't be able to see the discrete points. So I've covered all orientation space in every 2.5 degrees. And this is the number of points that are involved. So for cubic, I'm up, if I went 2 degrees, I'm up at about 100,000 orientations I need to cover. But if I went to triclinic and every 2 degrees, I'm up in the millions, and it gets very difficult as I go lower in symmetry. But we can do it in modern computers. And so the beauty is I'm going to show you an example here. Here is We did 10 scans on nickel on the same area, and we did them at different gains on the camera. As you increase the gain, you can get patterns faster, but they're noisier. So you increase noise. So what we wanted to look at is what is the effect of noise on our pattern. So if you do that, here is the as-scan data on the top row using our standard triplet indexing. We also have a feature called MPAR, which I'm not going to go into much detail here, but it also helps us improve indexing, and you can see there it's pretty good. But for the last one, for a very high gain, we still are struggling to get good results. Whereas with the dictionary, we do really well. Even out to 36, that final gain setting, we're actually able to get some pretty good good results. It's not perfect, but you can see the advantage the dictionary is on these really poor patterns. So here's an example where, once again, very high gain results. There's a dictionary over 2 degrees, and it took me about 20 minutes to do this with dictionary indexing. With regular indexing, this is a matter of seconds. So that just gives you an idea there. If you look at it, the orientations within the grains are not as smooth as you would get, and that's because of that 2 degree step function, basically, in our dictionary. But if you look at the indexing results, so what you have is noise on the x-axis and then indexing rate on the vertical axis. And you can see with the dictionaries, the top curve in green, at that very high gain setting, we're up around 75% of the patterns are indexed correctly. So that's really good. You can see with regular indexing, we're down around 5%. So it's a big improvement. Just as an experiment, I've also used it on multi-phase samples. This is a duplex steel with an FCC and a BCC phase. And so you have to run it. So basically you're doubling now your dictionary size because you got to do one for FCC and one for BCC. So it'll take twice as long. But it is doable, and you can see the deconvolution at the boundaries is a little bit different than our regular indexing, which I think is a little interesting. I can't say for sure which one's better, but I think the dictionary is a little smoother, which I think encourages me that might be a good approach for solving problems where maybe at the boundaries you're having problems. Just to get an idea of the dictionary spacing, so the Huff-based result is there at the left at the top row. At 2.5 degree dictionaries in the middle. If I go to 5 degrees, you can see I'm not sampling orientation space finely enough to really get good indexing. So I'm missing some orientations. The patterns are just too different to capture. The second row of images is what we call the inner product, which is the way we do the comparison. You can see the value, a high value in red is good, a blue value is bad. So you can see that we're matching much better at 2.5 degrees than we do at 5 degrees. So once again, that dictionary size, you have to probably at least get to 2.5 degrees, so that kind of tells you what you're working with. The better the angular resolution, the larger the dictionary, the lower the crystal symmetry, the larger the dictionary. Multi-phase materials require multiple dictionaries, so you can see this is going to get very computationally intensive. But it is doable. So if I'm getting good results with regular indexing, I wouldn't jump to dictionary indexing is my point. But if you have something that's really difficult, maybe dictionary indexing can help. We're also looking at dictionary indexing helping potentially with pseudosymmetry problems in some of the more difficult materials, but I don't have a lot of results yet that I have to show. One of the nice things is since we've implemented this in OIM analysis, we can use a lot of the tools that are already there to speed this process up. So here's my original, once again on the left. If I look at a confidence index map, the CI or confidence index is a measure of reliability of indexing. And so I could do a confidence index map. I can do some tools I won't talk about here, but red is good, blue is bad, a low confidence index. And so my 2.5 degree dictionary is there at the bottom. So what I can do now is instead of, some of the points in my original map are actually good. They look like they're good. We don't have to re-index those. So what we can do is, I did a little study to see which points are changing from the dictionary indexing. And you can see it's those points, if you look at the red curve on the right, it's those points with low confidence index that are ones that are changing from dictionary indexing. So let's just do dictionary indexing on the low confidence index points. So the idea here is I take my confidence index, I filter it, and I only index the ones that you see in black there. So those are the ones that are low confidence index. And so now I get the final result. So I'm going to combine my regular indexing there on the left with my dictionary index and the low confidence index on the right, and merge those, and you can see I get a great result. And the nice thing is now is instead of doing all the points, I've only had to do 37% of the points. Oh no, 63%. So I've saved quite a bit of time. And you can see the results are quite similar. So the one on the left is the merge, the one is if I do all dictionary. Now how does this work on other materials? So that's kind of an artificial case because we've added gain artificially to try to make bad patterns. But what if we have bad patterns because of other things that are inherent to the sample? So in this case, it's a heavily deformed magnesium sample. You can see the results here. You can see the as scanned versus the NPAR. We don't get much improvement with NPAR either. It's a really difficult sample. We have some tricks to try to improve the way the NPAR works, and we'll use those just to show the results. But here we go. We have the conventional on the left, NPAR in the middle, and dictionary on the right. You can see there's not a whole lot of difference. In fact, the dictionary may even be a little worse in this case, at least compared to the NPAR. So this shows you that the dictionary is great in some situations, but others not. So we're still experimenting and finding out the limitations of when it improves and when it doesn't. But the nice thing is we have all these tools available in OIM analysis, so we can do conventional, we can add in NPAR, we can do NPAR with dictionary and use all the tools at our disposal to get to the best result we can. And you know, this is a tough sample. We'll take what we get and we'll try to understand the materials based on it. And just to show this is all implemented in our OIM analysis software. So some conclusions from this part, the dictionary part, is it works really well, especially on extremely poor quality patterns is when it has its advantage. We can do higher efficiency by coupling it with the confidence index filtering and with NPAR. It is slow, especially as the symmetry gets lower. And most important, I showed this to somebody once and they said, oh, we no longer need to polish our samples. That's not true. Still, you want to get the best results you can, so please don't use this as an excuse not to polish samples. You'll get better results. In terms of some future directions, there's already some work going on using pseudosymmetry problems, and I'm excited to play with that in the future. Also looking at, can we improve the precision of our measurements through dictionary indexing? That's another area that's going on. And then there's more efficient computation schemes. In fact, there is a poster here this week from Foden and Britton and colleagues, that one there. And also, I know the group at CMU is also working on a different approach to indexing. So instead of comparing patterns, they do something in frequency space, something a little more complex mathematically. So another use of this is reflector optimization. So if you've ever had to get started when you've got somebody brings you a new material, you want to do EBSD on it, it can be really hard to get started. The first thing you'd do is you'd prep your sample, then you capture some patterns, and then the next step and the hard step is often building a structure file so that you can index those patterns. To do that, you need to know something about the symmetry, you need to know the lattice parameters. Ideally, you want to know where the atoms are in that crystal structure. And from that, you're going to calculate which reflectors are producing bands in the pattern. So where do you find this information? Well, there's various databases you can look at. You can ask your colleagues. You can look online. And eventually, hopefully, you can get a set of reflectors that will work. And like I said, you need to know the symmetry. And so there's two different ways to do this. You can try to use some X-ray data or some other version of data where you have the reflectors. Or you can use the atomic positions and then use that to calculate those structure factors. And from that, you know how to index. So why is it hard to do? Well, diffraction models aren't perfect. We know the kinematical one doesn't work all the time, doesn't match what we see in the patterns. If you're using X-ray data, that might not work at all because X-rays are different than electrons. Your observed material you're looking at may differ from that entry in the database. And that's still a challenge no matter what. But in the end, the selected reflector should correlate to the band use that the Huff transforms find, which may be different than what you find with your own eyes. So we usually have to do some manual optimization because what we see in the patterns doesn't match what we've predicted. And And this is a difficult thing to do, especially if you're new to EBSD. It's even difficult, frankly, for me to do. And I've been doing this for far too long. So our idea is to use the dynamic pattern simulation, and maybe we can improve and automate this procedure. So I'm going to show you a little comparison study we've done using kinematic structure factors versus dynamic structure factors. They're not truly the same thing, but the same idea. And then compare that with what we get actually from the Huff transform. So the idea here is we calculate a simulated pattern, and you can imagine doing this over the whole sphere for all symmetrical bands. We can come up with what we call a beta factor, which is basically the sum of the intensities. So it's somewhat like a structure factor. And then we're going to compare that to results we get from the Huff transform. Use the Huff transform to do some summing and so that we can compare the two. So here's an example for nickel. And you see the first column is the HKL, so that's which planes we're going to look at. The next column are these summed intensities that we call beta factors from the dynamic simulation. After that, you see the structure factors, and that's from the kinematical simulation. The little X's there, that column, are ones we had in our file to begin with. I just pulled a file from our database. And then you can see the results from the Huff, and then also some results from X-rays, threw in for comparison. And in this example, they pretty much follow each other, but not quite. You'll notice for the 220 and 311 bands, the dynamic predicts that the 220 bands will be a little bit more prominent, whereas compared to 311, compared to the structure factor calculation. But for the most part, they pretty follow each other, and that we expected that. This is a nice, simple structure. Let's go to something a little more complex, a rutile, titanium dioxide. And you can see here now that they are starting to vary more. If you look at the second and third columns, they are starting to vary a little bit more. And this one's kind of interesting because we were finding from this kinematic prediction that we should use that 310 band, but that's probably not one we would use based on the dynamic. So we started to look at those details and see what we would find. And in fact, if you look at the Huff transform did not find that band. So already our dynamical simulations given us a hint that we could do better with our reflectors. So we went through and looked at this manually to try to understand it. And if you look closely, we found that the Huff result more closely matches the dynamic result than the kinematic result. So this gives us a better starting point to get our reflectors right. We went away from the height or the strength of the reflectors. We went to how frequently they're found by the Huff transform, because that's more important in terms of indexing. So we compared it with actual data. So these are actual samples of rutile. We indexed 120,000 points. It's about 1,100 different grain orientations. And you can see the results over there. It's confusing to look at, so let me just highlight a couple of points. Here's the results from the dynamically simulated patterns. And this looks really noisy. But if you look really closely, dynamical ranking follows the Huff much better than the kinematic. And so now we can start to use these dynamical patterns to predict what reflectors we're going to find. And as another example, here's quite a bit more difficult material, olivine, forsterite, which is a particular type of olivine, orthorhombic. And what we found is this one predicted we should see the 311 reflector, and indeed that is the case. So it's just showing that this gives us a way to improve our normal indexing, not just our dictionary indexing. Just some things to think about. The Huff settings will affect these results. You can set your Huff so it tries to find narrow versus wide bands, and that will affect the ranking as well. And we also know, like I said before, that these experimental patterns don't exactly match the dynamically simulated patterns, so it's a good idea to spend some time getting things, comparing against some real patterns. And besides, your material, like I said, may not perfectly match the one that was in the database that we used to get started with from the beginning. And this is kind of what the software looks like. So it's a big, long summary. My point, the last one I think is the most important. A good practice is to set the Huff to find the bands in experimental patterns, create a set of dynamically simulated patterns, and then test the Huff on those simulated patterns to optimize your reflector list, and then confirm that on the experimental patterns. The nice thing about dynamically simulated patterns in this problem is we know the orientation. So it's something with an experimental pattern, we don't know that. We don't know that going in. Whereas the simulated pattern we do, and that's a big point that allows us to do a lot of kind of work with these patterns to understand them and understand how they affect our results. So one last thing I wanted to show you is background processing. And those of you who have been through one of our training courses, then you've kind of seen some of these slides before, but let me show you kind of what we're doing with the dynamics pattern simulation to improve it. So here's a nice pattern. This is what they look like before you do background processing. This is really tough. You can see the Huff peaks a little bit, but they're not really strong. So how can we improve that? Well, we can improve it through background processing. So we start out with a pattern from an individual grain. You can see it's pretty weak. We get a background from all the grains, a background pattern. We subtract the two, and we get a pretty pattern like that. Now, we can also do this through dynamic background processing. In this, we take a pattern, we blur it, we subtract the blurred one from that, and that gets rid of those intensity gradients, and we end up with a result like that. And that can be helpful for single crystals, rough surfaces, multi-phase samples, cases where we have a hard time getting either a good background or a consistent background. One issue is that any defects in the phosphor screen remain. It's quite a bit slower, but we can use it. So one of the challenges we have is with multi-phase samples, and this is kind of a theoretical example, but a good one. So we have here aluminum pattern, a tantalum pattern, collected the same amount of time. You can see the tantalum pattern is much stronger, and that's just because it's a better diffractor. It gives us nice patterns. And that comes into play with that factor I've circled there on the structure factor calculation. And if you see that intensity factor there, it's a function of Z, the atomic density. So that's why we get better patterns for things like tantalum, lower on the periodic table, than we do for something up higher like aluminum or say silicon or something like that. So if we can simulate these patterns, the first two on the left is a simulation where the simulation is done on the same scale. The next one, second column, we normalize it so that they're on different scales so that it pops out the aluminum pattern better. Now, if I average out 500 of these simulated tantalum patterns and average out 500 of the simulated aluminum patterns, at first glance, those backgrounds look pretty similar, but there's actually an intensity gradient between the two. And if you subtract the one at the top from the one at the bottom, you can see that there is a gradient. So what that means is if we were to do a sample that had tantalum and aluminum in it, our background would not be very consistent. It would lead to poor indexing results. So what we can do is we can now simulate the backgrounds and maybe use chemistry or some other way of differentiating to say, okay, let's use one background for aluminum and a different background for tantalum. In this case, this is just to show you that a simulated background gives just as good as results as an experimental background. So if I use a different one for the two, this is actually just kind of a theoretical result here, then you can get a very nice result. Just to show you that this matters, here's some patterns for some tungsten moly particles in a nickel matrix. You can see for the particles we're getting terrible results, and that's because the patterns first off are weak, but also our backgrounds are not situated for those patterns. If we use good backgrounds, then we can see the patterns and we can get good results. And now you can see I'm able to index those to individual particles just fine. So one of the questions I've asked myself is we've given this slide, I don't know, hundreds of times in different courses around the world saying this is how you do this. And I've always said, let's use at least 25 grains. I've never really checked that. It just seemed like a good number. But with the experimental patterns, or dynamic simulated patterns, we can test this. So here's a comparison against 6,656 simulated patterns. Here it is for 25. Turns out 25 is probably not enough. You probably ought to collect it from a few more grains. In fact, if you do about 500, it looks like you get a pretty close result to really random. So just something to think about when you're doing regular EBSD. But at least an answer to a question I've always had. In fact, if you look at this little graph, you can see here at about 100 to 500, somewhere in between there, you're going to get a good result. And so we have software now to generate background patterns, so you can use these in the cases maybe you got a single crystal and you can't get good background. Now we could give you a simulated background. So that's one of the points, just the points in red. Simulated backgrounds work. That's a good thing to know, and it also let us know that we need to cover larger areas with more grains when we collect our regular backgrounds. So in summary, dynamically simulated patterns are great. We can replicate the experimental patterns quite well. We're starting to play with them to do various things like dictionary indexing and picking out reflectors and generating backgrounds, but there's other areas we're starting to explore. In fact, we are introducing a new camera this week that's a direct electron detector camera, and it gives us very, very fine results. If you have time, there's a nice, I didn't put one in the slide, sorry, there's a nice picture around the corner here. It has a lot of detail. And the beauty is we're seeing things now with the simulated patterns. We can use that to study those background, or these new direct electron detected patterns. And we're seeing physics maybe that we didn't know we had. And we're missing things in the simulated backgrounds, or in the simulated patterns, but we're also picking up some things, a good confirmation that we can't see in the weaker patterns from a phosphor screen, lens, typical system that we use. So stay tuned, there's more to come. I think it'll be an exciting area that you'll see more and more stuff from that. And certainly you're welcome to stay and ask me more questions or some of my colleagues. If you're interested, I did most of this talk recently in a webinar, so if I talk too fast, which I always do, then you can get some more details there and look at some other things. So with that, thanks for your attention, and let me know if you have any questions.